programs and you have been able to attend.
Yeah, but I'd much rather be there in person. It's a shame that we can't be
and this is a nice place to stay.
Very good. Very good.
Yeah.
Okay.
Okay. I think so. Doreen. So with a nice introduction of Andy.
Yes. Sakshi, are you there? Can you start, please?
Yes, sir.
Okay, Sakshi, you introduce Professor Andy Way and start the program.
Yes, sir. First of all, Namaskar, sir, from India. And it's my privilege to welcome Professor Andy Way from DCU, Ireland. And he will be talking on machine translation in the age of AI. Professor Way obtained a BSc Honours in 1986, an MSc in 1989, and his PhD in 2001 from the University of Essex, Colchester, UK. From 1988 to 91, he worked at the University of Essex, UK on the Utora MT project. He joined DCU in 1991 and is employed as full professor. He was the recipient of the 2015 DCU President Research Award for Science and Engineering. And in 2019, he received the extremely prestigious Award of Honor from the International Association for the Machine Translation for his services to the community. Professor Way was principal investigator for the Integrated Language Technologies in CNGL until June 2011. When he looked a career break until December 2013 to work in the translation industry in the UK. On his return to DCU in Jan 2014, Professor Way acted as Deputy Director of CNGL and subsequently Deputy Director and co-applicants of ADOPT, the 100 million euro SFI funded Center for Digital Content Technology. Professor Way has secured grants totaling over 100 million euro with over 12 million euro directly from his own research. He has been lead researcher on 13 EU projects, bringing over 28 million euros. Professor Way served as president of the European Association for Machine Translation from 2009 to 15 and was president of the International Association for Machine Translation from 2011 to 13. He has been editor of the Machine Translation Journal since 2007. He is currently editing a series of 6 books for Springer in the area of machine translation, with 2 already published. Professor Way has published over 400 peer-reviewed papers and currently has a Google Scholar H index of 43, an I-20 index of 202, and over 6,800 citations for his research. He has successfully graduated 28 PhD students, 5 of whom have won Best Thesis Award, and 11 MSc students. He currently supervises 5 PhD students and 15 postdoctoral researchers. Professor Way's research interests include all areas of machine translation, including neural machine translation, statistical machine translation, example-based machine translation, rule-based machine translation, hybrid model of machine translation evolution, teaching machine translation, etc. Now, may I request you, sir, to kindly start your keynote presentation.
Okay. Thank you for those very kind words. That was a very nice introduction. I'm very flattered. So, obviously, we're all very busy at the moment, and I received an invitation from Doran and from Sivaji a couple of months ago to participate in your event. And because of the very strong links over the years that we've had between Professor Sivaji's lab and my own lab, I couldn't possibly turn this down. So I was delighted that I was able to find a slot in your busy program that I was able to talk to today. So many of my very best PhD students and postdocs have come directly from Professor Sivaji's lab. So it's a very strong link between our 2 teams. So I was saying to Doran there before we started, I participated 2 years ago, just over 2 years ago, in a similar workshop in IIT Patna. I was able to, obviously at that point, attend face-to-face. So and I had a very nice couple of weeks in India. We saw a lot of things in Delhi and in Agra, the Taj Mahal, and then we went to Kolkata, a very beautiful city, and then we managed to get up to see Everest in Kathmandu. So it was a terrific trip, and all the more regrettable that I am sitting in my study here in Dublin, and hopefully in a few months' time, we can see light at the end of the tunnel now with the end of the pandemic, hopefully in sight, and there may be a future opportunity for me to travel to Silchar and see you face to face. So anyway, let's get started. Machine translation in the age of AI. Well, I can certainly miss out on this slide because you've already said everything on this slide. So here is what I plan to talk about today. I want to convince you, if you need convincing, that machine translation is being used and will always be being used. So, there are people out there who say that machine translation is useless, and it's the job of people like myself and Sivaji to show people that actually it can be very useful. So clearly, you've had lots of other presentations during the week on deep learning and neural nets, on representations of words, for example, in word embedding, and even some talks on multilingual aspects. So some of what I cover may be a little bit fundamental, but I'm taking it from first principles so that everybody, hopefully, so nobody will be left behind. And it's clear from looking at the output of NMT systems that the quality of the neural engines is superior to what we were doing there for maybe 25 to 30 years, namely statistical machine translation. But along with this new paradigm, the onset of this new paradigm, there's been a huge increase in the hype surrounding neural machine translation. So I plan to try and show you how neural machine translation works today, and then address the important question of how translators, who are always going to be the primary users of machine translation, some of them now are afraid that neural machine translation is so good that it's going to take their jobs and there'll be no future for them, career-wise in the translation business. So I have given versions of this talk before to many sort of translator conferences because I think it's worth showing them that despite the fact that neural machine translation is undoubtedly superior to statistical machine translation, it still makes lots and lots of mistakes which a human would not make. And so there is plenty of scope for collaboration between people like me who build machine translation systems and human translators who use them. Let's continue on. So I don't probably need to convince you of the fact that there is so much content being produced these days, and a lot of it, the content is being produced by people like us on social media. We're producing tweets and Facebook posts and LinkedIn updates. So we are consumers of social media, but also producers of social media content. So of course, there are not enough human translators on the planet to translate everything that needs to be translated. So some people have estimated, for example, that 98% of content is never translated. This was these statistics go back a few years, but they're probably not too irrelevant today. And of the top 1,000 websites from the world's biggest companies and top brands, 45% are still single language sites. And there's lots of evidence to show that in terms of e-commerce, for example, people would much prefer to conduct e-commerce transactions through their own language rather than through some second or third language. So, there is still plenty of scope for businesses to take on board more translation and become more multilingual. Another similar quote there from about 10 years ago from Mark Lancaster, who at the time was in charge of SDL, one of the world's largest translation companies. And he said, around 90% of what currently could be translated is not being translated. So there's a huge amount of content out there which is not being translated. And clearly that's where some sort of automation has to kick in. So, in the era of big data, you can come up with some big claims and some big numbers. And here's a big number. So this came from, I think, the 2016 Google conference. So every year Google has its own conference where it showcases its services and products, and shows off really to the world about how good it is. And of course, it's the biggest, company, or one of the biggest companies on the planet. And, everybody these days has used Google Translate. So many years ago, people like Sivaji and myself, it was difficult for us to explain to people on the street what machine translation actually was. Whereas nowadays, everybody from my youngest child to my mother have used Google Translate or something similar. So here is a statistic from 2016 from Google showing that over 143 billion words, that's a huge number, 143 billion words have been translated every single day. Yesterday, today, tomorrow, the day after. That's a huge number, 143 billion words. That's 20 words per person on the planet. It's every single day. So, I don't have any patience anymore with people who tell me that machine translation is useless. You cannot tell me, this is one provider, albeit the single biggest provider of machine translation on the planet. But this is 143 billion words every single day translated via Google Translate. So if we add in, all the translation from Bing and all the other MT engines, Amazon Translate, plus all the other MT systems which are out there, it's a huge amount of content being translated every single day via MT. So people are obviously finding, the output from these engines to be useful. So there are a range of use cases out there, and many more still to be discovered, where machine translation is of vital importance. And machine translation investment is on the rise. So if you just go down, this is quite a new chart, comparing the expenditure in 2020 versus 2019 on a range of different application areas. So if you go down to the fifth topic. So machine translation is coupled in with speech recognition, computer interaction, and dialogue. But you can see now, the area in which MT is situated is receiving a huge amount of funding in 2020 compared to 2019, and it's bigger than even money laundering, anti-fraud, fraud detection, fraud prevention. So machine translation and natural language processing in general is increasingly important. So let's go back a few years to when neural machine translation came in and started to show its improvement in performance compared to the previous paradigm, statistical machine translation. And associated with that was some hype. So in the age of AI, there is a good amount of hype and overhyping, the performance capabilities of the systems that we build. So if you just look at the title of this this paper by the authors of the Google NMT system, bridging the gap between human and machine translation. Okay, so this is the archive paper, 8th of October 2016. You can see that. So bridging the gap between human and machine translation. So people like me who've been teaching machine translation and talking about machine translation for 25 or 30 years, all we're trying to do all the time is kind of level the playing field, to talk contemptfully about what MT can do and what it can do, and where we need humans in the loop, and where and application areas where machine translation, the raw output is good enough. But when translators see bridging the gap, they start to, understandably get a bit afraid. So the sorts of things you start to see then around this time were claims from journalists like it's nearly indistinguishable from human translation. It's as good as a human translator. It's a miracle. It translates as well as humans can. It's a major breakthrough. It's approaching human level accuracy. So, of course, understanding neural nets and AI and deep learning is quite difficult, even for some quite clever people. And journalists, find it hard to understand, a paper that's written by the authors of the Google NMT system. So they have to take, the title as being accurate, whether it was supplied by the authors or the marketing department in Google, I don't know. But nonetheless, that paper exists with that title. And then you start to see, journalists getting excited. And when journalists get excited, translators start to get frightened. So is it really as good as human translation? Can it compete with human translation? Will it replace human translation? Will interpreters and translators' jobs die out? Will the language barriers which are being removed cause jobs to be lost? What's the future for translators, given this, this onset of this new paradigm? And of course, things have continued along that road. So we saw that the Google claim was, bridging the gap. But then in 2018, so the lead author here, Hani Hassan, was a PhD student of mine, very modest man, very gentle man, and I would be able to assert quite strongly that he would not have chosen this title by himself. So I'm assuming this is the Microsoft PR people trying to compete with the Google PR people. So for the Google paper, we saw bridging the gap, and here we see achieving human parity. Okay, so again, the leader of the team, Chris Wendt, so there was lots of criticism about this, the title of this paper. But Chris Wendt, who's the head of that team, he said, look, it's a very narrow claim. It's only on news, and it's only on Chinese to English, and it's only approaching human parity. It's not the same as human parity. But people only see the words, the two words human parity jump out. And again, we see similar claims in the press. It reaches a historic milestone, matching human performance, achieving human parity. It's as good as humans. It's achieved a milestone. Human parity has been achieved. And of course, people like myself in our team, we unpicked these claims. Microsoft were very good to release all of their data, all of their human judgments, all of their reference translations, and the output from the MT systems. And we were able to show that actually, once you dig a little bit deeper, that human parity actually was not achieved. But nonetheless, partly the damage has been done because the translators start to get worried about their situation. And again, here's a post from SDL where it talks about achieving human performance. It's cracked Russian to English neural machine translation. So in my knowledge of English, and I'm a native speaker, been on the planet for a good few years. When you crack something, you have solved that problem. Now, Russian to English is a difficult language anyway, because we're dealing with two different alphabets, like we would be with Hindi and Bengali and English, for example. So cracking something really means you have solved the problem forever and a day. And clearly, this is not the case with this SDL claim. And here's an even newer one. A deep learning system has reached news translation quality comparable to human professionals. And I know, one of my old postdocs, Antonio Toral, who was a professor in the University of Groningen in Holland, in the Netherlands, has unpicked the claims at WMT 2019 of superhuman performance, the MT systems even outperforming the human beings. So of course, these claims have to be taken with a pinch of salt. We have to think about the metrics that were being used to measure the quality of the MT output, and also what humans are being compared here. Are we talking about human professional translators with, many, many years experience, or are we talking about, apprentice translators being sort of coached at university, or what? I think you can see that these headlines are causing some sort of grief among human translators. And it leads to, as we've seen before, whenever SMT came in, large claims, came in from those practitioners over, the old rule-based paradigm. So this thing is, is fairly cyclical. We've seen it before. And it means that, for people like myself, we have to, again, sort of calm the water and try and talk to translators and say, look, okay, the quality is continuing to improve, but there will forever and a day be a place for humans in the loop. And it's been the case that machine translation has been overhyped for years. Even when it first came in, a tiny little experiment in the University of Georgetown with a very, very limited vocabulary and a very small number of sentences for English Russian. Again, people started to get all excited. And then it was all doom and gloom with the publication of the AICTE report in '65 saying that machine translation and language processing in general could never be as good as a human. And then rule-based processing came in and things started to pick up a little bit. And then statistical machine translation kicked in, and obviously, the hype kicked in again. Then we realized, a bit of, a reality check came in around, in the 2000s. Then, of course, neuromachine has kicked in and the hype has exploded. So this has been a pretty cyclical thing. And, some of us who've been around in the field for a long time have seen this thing for years. But of course, machine translation, neuromachine translation in particular is pretty good these days. So just want to feature some results from a talk that was given in 2016 at EMNOP by researchers from the University of FBK in Trento in Italy, together with the University of Amsterdam. And, they focus on, so the IWSLT, one of our shared task platforms, 2015, English to German, a difficult challenge. English to German is quite difficult. So we're translating from a morphologically poor language into a morphologically rich language, German. And this is quite difficult with different word order. Typically in German, the verbs come at the end, whereas in English, the verbs come somewhere in the middle. And they had two criteria here. They compared the results from the best neural engine against three different types of statistical machine translation system, both in terms of pure output quality, what was the blue score, for example, and, the ability to actually post-edit the output. So here are some results. And again, I won't spend too long on this, for reasons of time. But if you take the top graph, essentially, so TER, translation edit rate, is an error rate. Okay, so the lower the score, the better. So you can see that neuromachine translation is better than each of the other three SMT systems. So the overall quality is better. If you take the left middle chart, the green chart, this is looking at the number of lexical errors, lemmas there you can see, and there were fewer lexical errors made by neural machine translation compared to all three SMT systems. The pink chart on the middle right is calculating the number of shifts, the cut and pastes, if you like, the number of word order errors. And again, those are significantly less with the neural machine translation system. And the bottommost chart is looking at morphology, words and lemmas. And you can see that, with the NMT system, there are fewer morphological errors as well. So this is demonstrating that even in 2016, that neural machine translation was starting to show its superiority over SMT. But of course, we know that statistical machine translation, we needed a lot of data, and now we need even more data to build very good neural machine translation systems. And here's a chart from a paper by Philip Kern and Rebecca Knowles from 2017, where they built two SMT systems and a neural engine, and you can see that for less than 1 million words, the SMT is vastly superior than the NMT system. So this has impact on low resource conditions. You can see here the quality for NMT starts out relatively low, outperforms the baseline SMT system around 15 million words, and then beats the SMT system with a very large in-domain language model eventually, once enough training data becomes available. So the field for a long time thought that NMT required a lot more data than SMT, but I'll just point you at a paper from Rico Senric and Biao Zhang from 2019, which showed that actually, in low resource conditions, you can get better performance with NMT with much lower amounts of data than was previously thought. So that's a paper worth looking at. So let's take a quick look at how NMT works. And of course, neural machine translation works with neural networks. So this may have already been part of the previous presentations during the week. So if it is, I apologize if it's too simplistic. But if there are people in the audience who don't understand this stuff, hopefully you will be able to walk away with some understanding of how the underlying technology is working here. So essentially, you have an input layer and an output layer. Your input layer is your words and phrases in machine translation, for example, in the source language, and your output layer would be your representations of the target language words and phrases. Okay, and then we have either a single hidden layer or multiple hidden layers. If we have multiple hidden layers, then we're talking about deep learning. If we have a single hidden layer, this is not deep learning. This is straightforward neural network technology. So that's all we have, and you can see that the nodes at each layer are connected to all of the nodes in the previous and the subsequent layers. Okay, so you can see that even in this very simple network, there are quite a lot of arcs between the nodes in the various layers. Okay, and each of these arcs has a weight on them. And essentially what we have to do is come up with, after many millions or billions of training iterations, we come up with the optimal set of weights for our model. We then freeze that model after we've trained it and trained it and trained it. It's the best it can possibly be on the dev data, and then we expose it to new input from our test data, and then we measure the performance. So essentially, what we have is, so we turn our words, for example, into numerical representations, and we put those into a vector. Whatever the input is, whether it's text or speech or features from an image, whatever it might be, all of these are converted into a mathematical representation, i.e., a vector of input nodes. Okay, we then have a vector of hidden nodes and a vector of output nodes. So what we would need for machine translation is to take that representation of the output and turn it into, let's say, a string of words, in the target language for machine translation, or a string of words, for example, for automatic speech recognition, or a caption for an image, whatever it might be. So we have to, there's some pre-processing and some post-processing to turn the input, whatever it was, into a mathematical representation, and the post-processing is required to take that internal representation of the target output and turn it into, output which is understandable by us as human beings. We have two matrices, a matrix of weights connecting the input nodes and the hidden nodes, and a matrix of weights connecting the hidden nodes and the output nodes. And of course, if we had multiple hidden layers, we'd have matrices of weights connecting the nodes in one hidden layer with the next hidden layer. So you can see that, over time, there are a number of nodes in the input layers, the hidden layers, and the output layers, and the number of arcs which connects all of those nodes, increases significantly. And our job, as I say, is to optimize the weights during training on those arcs. Okay, so let's take an example of image recognition. Okay, so because the fundamental architecture underpinning machine translation is the same. So it's sequence-to-sequence learning. So here we have a sequence of images and a sequence of labels, and we have to predict the right label for the image. So we have a bunch of training data and a bunch of test data. So we have four possibilities here in this toy example. We have cats, owls, dogs, and lions. And we're going to train it up on that training data, and then we'll test it with that brand new input, which has never been seen by the system before. And we'll see what the frozen neural networks performance actually is on this brand new test data that has never been seen. So as I say, we train the neural network by iteratively updating the weights. We can start, there are many ways in which you can start, assigning weights to each connection, but one way to do it is just, randomly to start off with. We show the network examples of inputs and expected outputs. So for MT, we would be showing it, a source sentence and its expected translation, its human reference translation, for example. We might calculate the blue score differential between what the MT system outputs versus that reference translation, and percolate that error all the way back through the network, update the weights, and pass the same translation example through the system many, many times, millions of times, until we get the best blue score we can for each of the sentences that we're playing around with, using back propagation. And we keep updating the network until the network is working the way we want, or until we have kind of run out of patience, or the customer actually wants to see the performance on some real data. So here's an example. We have an input representation. Here's a picture of a dog that gets turned into some vector representation, perhaps some sort of grayscale representation. There'll be bits of black and bits of gray and bits of white and bits of other stuff. And then that gets passed through the network. We present the network with the label that we expect, which is dog. We see that the output from the neural network first time around is cat. We percolate that error all the way back through the network, update the weights, and start the whole process off over and over again. And after very many training sessions, what we would hope is that we pass this representation of a dog through, and that the output prediction by the neural net is the same as the label that we have provided. So now there is no error because its prediction is the same as the gold standard label. So we don't have to update the weights for that particular image. And we do that, over and over again for multiple images. And then we can expose the network, which is the best it possibly can be, with our test data that you saw on some slides a few slides ago. So here is an image that it hasn't seen before. So we pass this image, this representation of this image of a cat through the network, and it accurately predicts cat, which is great. So we got that one right. We can do the same with the picture of the owl. Again, you can see that the output prediction is the same as the label. So again, that's another one that we got right. Here's a dog, picture of an Alsatian. Again, it predicts dog, and that's the same as the label. So we got that one right. And then we have our tricky one. So if you recall, our training data were all big daddy lions, big, male lions. And of course, this little baby lion doesn't look too similar to the training examples. So here you can see that, while the label associated with this image is lion, the system actually predicts cat. And that's not an unreasonable prediction, given that it looks, a baby lion cub looks much more like a cat than a big male lion. So we got that one wrong. So overall, our accuracy on this very toy example was 75%, and now we can publish that performance for our system. So, going back to neural machine translation specifically, let's compare how neural machine translation works, compared to the old paradigm of statistical machine translation. So, machine translation, where it's corpus-based, we have some sort of learning paradigm. We have a large corpus of English and German parallel sentences, and the system, just starts to infer correspondences between the source and the target text. And that's why, the larger amount of data usually leads to a better model, because it's got more evidence in favor of some of the inferences that it makes regarding, the source and target language. So if we just go back a few years and think, how did phrase-based SMT work? Well, essentially, what we did was we have a source sentence like we have on the screen here. And that was split up into words and phrases. And then we hypothesized, potential translations at the word and phrase level. And we collected those together. And then using the target language model, we tried to sort of smooth that into the best possible target language utterance that we could produce. Whereas in neural machine translation, okay, what we have at the end of the encoding process, and I'll show you some of this in a minute with another toy example, is a complete model of the whole sentence. So after training, after the encoding process, after looking at the whole, or after doing all of the source language processing, we take the state of the network at that point and we pass over that hidden state of the network wholly to the target side, to the decoder, to try to hypothesize what the best target translation should be. So in SMT, we never had a model, we never had the full context of the source sentence, but we do have that in NMT. So when people ask me, what's the single, biggest reason why neural machine translation outperforms SMT? That's the answer that I give, is because we have a model of the full context of the source string in neural machine translation. We never had that in SMT. So I think that's one of the reasons why neural machine translation could be producing better outputs than SMT. So here's, up until recently, the state of the art in neural machine translation was we had an encoder model for the source language, the cat on the mat, for example. We had a decoder, okay, for the target language, and these were separate neural nets. So we have a source language neural net, a target language neural net, and we had this attention model, which essentially looked at other words in the string and said, look, while you're trying to think of the best translation for this particular source language word, you might take this other source language word into account, and that may help you produce a better target language word. So the example we always give is bank. So Bank of the River and the financial institution. So if the attention model can look ahead and find the word water, well, then we might think, okay, the translation of bank here could be riverbank. And if we look ahead and we find the word money, for example, then we could disambiguate that English word bank into financial institution, where the target language makes those differentiations. So that was the use of the attention model. So for a long time there, for a number of years, this was the state of the art, an encoder decoder versus attention neural machine translation model. The state of the art today is called a transformer model, which focuses pretty much entirely on attention. I'm not going to talk about that today, but at least here, I think you can understand that here we have three neural networks, one for the source language, one for the target language, and this neural net, which is looking at essentially, helping produce accurate word alignments and enabling sort of end-to-end translations. Where you have one word in the source language, and maybe that's translated as two words in the target language, or vice versa. So that's what the role of the attention model was. And the trouble is, of course, these networks, balloon very, very quickly. So here's a network for just, recognizing handwritten single numbers from 0 to 9. Okay, you can see already, that's a much less complex task. All of the post offices around the world, use a system like this today to recognize our handwriting, our handwritten addresses on the front of an envelope that that we're sending off to somebody, to our target correspondence. So this works very well, but you can see already how complicated it is for quite an unsophisticated task. Okay, and new use cases are emerging all the time. I've got my tongue in cheek here a little bit. I saw this the other day. 2020 is only a few months ago. Arlington man arrested after trying to rob a bank using Google Translate. So this guy in the US, he brought his laptop or his phone. He had Google Translate on his phone, and he didn't speak English, and he wanted to tell the cashiers behind the counter that this was a bank robbery. So this is a new use case for machine translation, bank robbery, and I assert with some confidence that it would be quite difficult to see a human translator agreeing to this work. No human is going to walk into a bank with a bank robber and help him rob the bank because he doesn't speak the language. So should translators be afraid of neuro machine translation? Okay, so we're going to look at a range of other tasks, including machine translation, and just examine, how good these AI models are at sort of making the right predictions. So the nice thing about these AI architectures is no matter whether you're talking about machine translation or ASR or caption labeling or image recognition, the same underlying technology, the same neural architecture is being used here. So if we can see that performance in one area is less than we might expect as human beings, that may give some translators in our space, for example, some confidence that neural machine translation is not actually going to put them out of a job. So here's an example. Again, I've shown this. I like showing this example. We have some examples of labradoodles, little dogs, and examples of fried chicken. Now, if I said to you, in order to pass this course, okay, you have to show me which of these instances are dogs and which of them are fried chicken, all of us would get 100%. Okay, this is not a hard task for us as human beings, but it's a very, very difficult task for a neural architecture. Here's another example. I think this is a bit harder because some of these muffins look cunningly like chihuahuas, and some of the dogs actually look a little bit like cakes. So, some of us might not get 100% on this one. But again, this kind of adversarial learning, showing examples which are very difficult for a network to try to kind of decode is a strong sort of sub area in sort of neural language processing, and you can see that this is maybe slightly harder than the last one, but it's still reasonably easy task for us as humans to look at. Here's one. This is a real example of a caption labeling system. So the boy is holding a baseball bat. Well, I don't know whether that's a boy or a girl, for example, but I know he's not holding a baseball bat. Yeah. And why somebody would think that, why the system would think that you would have a baseball bat in your mouth, I don't know. So again, this is a mistake made by the neural system. Here's an example. These are two new examples from just this week. So a brand new paper produced by OpenAI, the OpenAI consortium, called Multimodal Neurons in Artificial Neural Networks. And what they're trying to find out is how individual neurons in the model actually work, or under what conditions do certain neurons fire with greater weight than in others. Okay, so it's indubitably the case that in neural machine translation, for example, that we can see from the output that the neural engines are working better than the statistical engines, but our level of understanding for people like Sivaji and myself, who'd like to understand what's going on, our level of understanding has decreased because we are not so clear about what's going on internally. And what these guys in OpenAI are trying to do is explore exactly that. So here's a picture of an apple, and here are the results after the recognition process. So it pretty much correctly says that this is a Granny Smith, a particular type of apple, and it's not an iPod, and or it has very, very small confidence in its prediction that it may be an iPod. It's not predicting that it's a library or a pizza or a toaster, but it may have some slight chance of being dough. But you can see 85, 86% is a pretty strong recommendation that this is an apple, okay? And what they do in the next slide is they take advantage of the fact that these neural systems are good at reading. So if they just stick a label on this, on this Apple, which says iPod, okay, and they retest, now you can see that its prediction previously was 85, 86% that it was a Granny Smith. That's gone down almost to zero. And now it thinks just because it can read iPod, that this really is an iPod. It's an Apple iPod, not an Apple. So you can see it's quite easy to mislead these systems. So going back to machine translation itself, here's an example that I've cited in a couple of papers that I've written. This is a real example that no longer works. Google Translate have fixed this, but going back to 2017, here's a German example. You don't really need to look at, you don't need to understand German to understand this example. All you need to do is look at the English translation. The economics of economics, brackets, including economics, brackets, is a part of economics. So what's happened here? Okay, first thing to say is that's a sentence of English, okay? Syntactically, that does not violate any sort of rules of English. So from a syntactic perspective, that is a sentence of English. But it's not a sentence of English that anyone would ever utter, okay? So it's semantically malformed. And the reason for that is because the attention mechanism that I pointed you at in one of the earlier slides has over-attended to the fact that in many of the German words, okay, economics appears to be important. So what it has done here is it recognizes the importance of the concept of economics, and it puts it too many times in the translation. So as I say, Google Translate, if you type in this translation, it won't give you this. Sorry, if you type in this source sentence, it won't give you these. It won't give you this translation anymore. But it did it at one point. So it's interesting to see how the system actually worked at that time. Here's an example from a conference I was at in 2018. Back when life was normal and we were able to meet face to face at conferences. And the example here in the talk is the third one. Is the one that I want you to focus in on. So the Spanish, so Spanish to English, okay, and the Spanish it says "Por qué no tengo servicio de internet?" Because I don't have an internet service. And then look at the NMT suggestion. The room was very clean and the staff was very helpful. So it's recognized that, in a hotel scenario, you would have internet connection. And it knows that, again, that we as human consumers of hotels, we like, having clean rooms and very helpful staff. But the suggested translation has nothing at all to do with the source string, okay? It has something to do with the overall context, i.e. hotel situations, but the translation has just been, it's just been, gotten out of nowhere. It's got nothing at all to do with the source string. So I have suggested that, there are some LSPs out there, some companies who are trying to save money by using monolingual post editors. And if you read that English sentence, the room was very clean and the staff was very helpful, you would say, yeah, that's a good sentence of English. But if you don't understand the Spanish input, okay, you would not be able to say that that was a bad translation. So for those companies who are trying to save money by using monolingual post editors, I think neural machine translation has sounded the death knell for that particular part of the translation process. Yeah, it's probably the case, and people assert this, that if you are to correct neural machine translation errors nowadays, you probably need to have the competence, which is very similar to that of a professional translator. But of course, not all machine translation errors are machine translation errors. So if you look at the headline on this article, translation errors force Osaka Metro websites offline. What actually happened here in this example was that the names of the stations on the Osaka underground, the metro, were translated into English so that nobody knew what station they should get off at. Okay, But of course, you know, what they should have made sure of is that those place names were not translated at all. You know, we need people to learn how to use machine translation properly. And sometimes machine translation is blamed for things when it shouldn't be. So it's great that translator training programs exist, but you know, project managers who work for translation companies, they also need proper training. So what should have happened in this example, prior to machine translation, those named entities should have been sort of surrounded by do not translate tags, so that, you know, the rest of the sentences was translated, you know, by the MT systems, but the place names remained intact. It would be like my name, my surname, for example. You don't want my surname to be translated. You know, my surname is a regular, you know, word of English, but you don't want that translated. My name in any foreign language is Andy Way, not Andy something else. You know, so, you know, we don't want all sorts of weird and wonderful target language translations of people's names or place names or whatever. Here's another example. This was a label in a T-shirt, and again, it's German. But the point I want to, you know, the point of this example is the top right example, trockene Wohnung. So, you know, for those of us who, you know, possess any clothing, you might look at the label, okay, and sometimes it would recommend that your jumper, for example, that you need to dry it flat, because otherwise it would sag and it would become too big and it wouldn't fit you anymore. So instead of drying, so dry, flat, okay? So here, flat, the adjective, has been translated into flat noun, okay? i.e. flat meaning apartment. So this means dry apartment instead of dry flat. So, you know, the instruction has been, you know, mistranslated, you know, probably by machine translation there, but it should never have been translated by a machine translation system in the first place. Here's a nice example in Ireland, you know, so you can see at the bottom, footpath ends in 40 meters. So you can see 40 meters in, so, you know, all of the signage in Ireland has to be in Irish and in English. So the English was footpath ends in 40 meters. And what you see on the top for Irish, it says 40 meters, which is grand, which is fine. And then Asgwelga means in Irish. So what the project manager has said was they have put Asgwelga in and said, look, you know, this is an instruction to a translator to translate footpath ends into Irish. But somebody has seen the Irish words there and assumed that Asgwelga means footpath ends in and has made the sign. And of course, that's, you know, wholly incorrect. You know, so again, these are all human errors, not machine translation errors. You know, the people using the machine translation engines were not educated enough to use the machine translation systems correctly. And of course, you know, we humans get all sorts of things wrong. Here's a nice example from the US of a sort of polysemy error. So you can see these signs which say reserved for green vehicles. And clearly what that means is, you know, new kind of electric cars or hybrid cars, which are not, you know, outputting lots of diesel fumes or petrol fumes. So if you have a new electric car, you can park in that slot. But the guy who's driving this pickup truck has misread the sign and said, okay, I have a green truck, I'm allowed to park here. So humans get things wrong as well all the time, okay? And of course, machine translation is still hard. Even though we're making progress with neuro machine translation, you know, there's still a lot of things for us to do. And the other thing it's worth noting is that, you know, many translators are already very well disposed towards technology. You know, the technology is really just making good translators better. You know, the technology is not taking care of the translation per se. There are certainly cases where raw MT is good enough, and there is no space for a human translation to post-edit that translation, for example. But, you know, the technology, you know, and people like myself and Sivaji who are building machine translation systems, you know, we are building those systems to try to help machine translation professionals become much better than they currently are, either faster or make their translations better. You know, we're not trying to put anybody out of a job. But there's still some resistance. This is an online conference I attended just before Christmas there in December, the second CEF e-translation conference. And there was a poll conducted during that conference. And you can see here, you know, the question, do you use or plan to use any automated translation system, e.g. e-translation or any other machine translation system? So quite a lot of people said, yes, I currently use one. Many people said, yes, I plan to use one in the future. But there were 7 people, 6%, who said, no, I do not use and do not plan to use one in the future. So that's quite a strong, you know, assertion by those 7 people. Now, I can't be sure that all 7 were human translators, of course, but it's still interesting, I think, that 7 people who attended the conference, and the conference was on translation and machine translation, they decided that they would never, ever use machine translation, not today or any time in the future. So even if machine translation continues to improve, these guys are so sure of their opinion that they're never ever going to use machine translation. So that's quite striking, I think. So what about the overall impact on translators? So of course, you know, whenever we are looking into the future, it's very hard for us to know with any certainty. But you know, people like myself, when you're a professor at a university, these are the sorts of questions people ask you. And whenever you write a proposal for funding, you have to try and predict, you know, what's going to happen in a few years' time. So here are my, you know, I'm gazing into my crystal ball here, and these are my, you know, predictions as to what the impact on translators might be over the next few years. So my first assertion is that translators will post-edit fewer machine translation outputs. So translation professionals are quite used to having no help at all when translating a particular source segment. So if you're using a CAT tool, you know, you have a high fuzzy match level in your system. You know, for many input strings, there will be no target language fuzzy match suggested for the translator to assemble into the correct target translation. So machine translation has been used wrongly in the translation business. You know, machine translation has been used for every single source sentence. And some sentences are obviously harder to translate than others. And occasionally human translators see examples where the machine translation system has gone terribly wrong. And then they see, you know, crazy mistakes and they go, machine translation is never going to be of any use. It's no good for me. It's absolutely hopeless. So they think that machine translation is no good, is it makes stupid mistakes that almost no human would make. So I think we have to get better at only showing our MT outputs when we have confidence, or the MT system itself has confidence, that what we actually propose to display is actually a reasonable translation. I think there'll be increasing demand for spoken language translation and multimodal translation in general. So my kids nowadays never type a query into Google. They just talk or shout at Siri. And around 20% of all Google's search queries are now conducted through voice. So we have to, you know, move with the times and deal with the particularities of speech. Otherwise, we'll be left behind. More literary translation will involve MT. So I've worked with Antonio Torral on literary translation, perhaps the last bastion for human translators. But we have shown in our work that, you know, machine translation could be useful even for the translation of literary works. Machine translation will improve for, you know, difficult languages and resource-poor scenarios. So many people are working on neural machine translation, or pretty much, you know, everyone is working on neural machine translation nowadays. So you will continue to see breakthroughs, and there are techniques like back translation which are helping resource-poor scenarios. So you know, these things will continue to improve. Interactive machine translation is improving all the time. That's where, you know, the MT system has output, you know, 1 or 2 words, or knows what the translation of the first 2 or 3 words is, and then it will, you know, offer you some sentence predictions to flesh out the rest of the sentence. So instead of you having to type in all of the rest of the words, you know, it's just a large language model, if you like, you know, and you know, the Spence Green and his company Lilt in the US have made a business model out of interactive machine translation. And adapting machine translation to translator edits is easy and helpful. We've done this ourselves. in the past. And, you know, after the human translator has post-edited maybe 200 or 300 sentences, we can model that and learn how the human translator herself is actually translating, or how she prefers to use certain words over words that perhaps the machine translation system itself is suggesting. And there we can overwrite the default translations from the MT system with the preferred human translation translations, and she can see immediately that the edits are useful to her as well as to the MT system, and that will encourage that particular human translator to continue cooperating with the MT system. Of course, ultimately, you can't do good machine translation, you know, without input from the linguists and the translators. So where does the translation data come from in the first place? You know, if we don't have translators, we don't have any machine learning. These parallel sentences come from human translators in the first instance, as you can see there on the top right of the screen. So we need the help of translators all over the place, you know, for the data in the first place. You know, machine translation is hard. You know, just because we've adopted a new paradigm, the problems don't become any easier. We need more data. We need human expert translators to verify the output of our MT engines. So I can build a system for any pair of languages. I can build a system for English Hindi, for example, but I don't speak Hindi. So I need some human experts to tell me, you know, whether the Hindi which has been produced is good Hindi or bad Hindi. And if it's bad Hindi, what errors the system has made, so that I can go back and correct those errors in future iterations of that system. We need them to compare, you know, versions of our MT systems to show us which one is better than others. And, you know, there are many instances today where human translators can still be of much use to us machine translation developers. So I love translators. Without translators, we wouldn't have the training data in the first place, you know. So, you know, translators themselves are vital to all of this machine learning effort. You know, all of the data that we use has been produced by human translators in the first place. And based on that, we can start to build our models. Without that human produced data in the first place to prime our models, we couldn't even begin the process. So I'm getting close to the end now. Machine translation quality is improving all the time. That's beyond any doubt. I think, you know, this is an opportunity for translators at the moment, because I think those companies who pay translators to post-edit machine translation output are probably a little bit beyond the times. They have a rate card for various language pairs, and I doubt that they would have updated those, you know, based on the improved performance of neural machine translation over statistical machine translation. So hopefully the MT is translating more stuff better than it used to for those human translators, so they have to post-edit less and still get paid the same. So there are still some cases where, you know, in low resource cases, for example, in low resource scenarios where the results are not absolutely clear cut that neural machine translation systems are better than statistical machine translations. But by and large, you know, neural machine translation is the new state of the art. As I say, everybody's working on this nowadays, so new ideas are coming out every week. And, you know, the translation industry is eager to improve, you know, our MT systems to minimize costs. But I think, you know, translators are starting to push back. You know, that cost cutting has probably gone as far as it can, and new, fairer ways of paying translators, like paying them by the hour rather than paying them by the word that they translate, are starting to come in as standard. And my final really assertion is that, you know, the hype around neural machine translation must be treated cautiously. People, you know, when technology is overhyped, you know, people like me have problems, because people come to me, you know, journalists phone me up or consultants phone me up and say, okay, when will machine translation replace humans? And I say never, and they don't like that answer, but it's an answer that I truly believe. So we need to be cautious about the claims of the new technology. You know, so finally then, I think this is a good time to be a technology advanced translator. Machine translation quality is improving translators' speed and quality. it's translating more and more content, and not just text needs translating. I showed you that at the very beginning. There are a huge amount of opportunities, to translate more data. As I say, fairer rates of pay are coming in, and the ethics around machine translation and translation, in general, are starting to be debated. So thank you very much. That's my last slide.
So participants, anyone who wants to ask question?
Professor Andy, I just have a question. Is there some way to figure out the real bottlenecks where the neural machine translation or the statistical machine translation, how do we figure out the real bottleneck in these two mechanisms?
Yeah, that's a very good question. So as I said during the talk, so we all understand by looking at the output that these neural engines are better than the old statistical paradigm. But our level of understanding is lower now because of the neural technology. So lots of things are going on inside the networks that we don't understand. So people are trying to, there's a lot of people working on sort of data visualization and visualizing what's actually happening at different layers and different nodes in the hidden layers in the network. But I think at the moment, Doran, the only way really is to play around with different training data and see what the output translations, how the output translations differ, and then try and work out, yourself as an expert speaker of the target language, what has happened with this new model versus the previous model. And then, we might get some insights that way. But at the moment, I'm sure this will be solved or greatly improve over the next 5 to 10 years, because as I say, everybody is working on neural machine translation nowadays. Almost nobody is working on statistical machine translation. So, it's just, we shouldn't forget that neural MT has only been around for the last 5 or 6 years. The models or the predicted models have been around a lot longer than that, but we didn't have the GPU clusters and the hardware and the amount of training data around in the 80s, if you like, to build these models at that point. We shouldn't forget that, people get very impatient very quickly and say, okay, what's going on? What's going on? We need to understand this. Yes, I share people's frustration, but, I think this problem will be solved just because of the sheer number of people who are interested in solving it. But it's admittedly a bit of a logjam at the moment. It does hinder our understanding. And when, there are people like you and me and Sivaji who, are paid, we're paid by our universities because we understand difficult concepts and we try to, teach that to our students. It's especially frustrating for people like us who like to understand things and like to understand and explain what's going on kind of under the hood. And at the moment, unfortunately, it's very difficult for us to do so. So it's a very good question, and it's not one that I have a real solution for at the moment.
Okay, my second question is on one of the slides there, we saw the performance comparison between the SMT and NMT, and SMT are performed for the low resource languages, and NMT keeps on improving as we increase the data size. So, but we see that many of the languages in the world are all resource constrained. So, what is your advice? Shall we still keep on using SMT until we reach that benchmark as compared to the NMT for the comparison of performance?
Yeah, again, Doran, that's a very good question. I don't know whether any of you who are participating today are on Twitter, but it's appropriate to say that over the last couple of days, I've been having an argument with people in Microsoft MT about the provision of language pairs. So, for example, my specific problem with them is that if you look up the Microsoft engines, the source and target languages, one of the languages that they support is Klingon. So Klingon, if you remember, if you're old enough, Sivaji and myself perhaps might be the only people in the room who remember Star Trek, from the 70s, and one of their enemies were the Klingon race from a different planet. And of course, there are people out there who like to speak these languages, but so Microsoft supports a language like Klingon, but it does not support a language like Hausa, which is spoken in sort of northern Nigeria and in that region, which has over 100 million speakers. And it appears that some of these companies will produce machine translation systems either because they're paid to do it or just because they think it's fun, but they will ignore some of the major world languages. But the problem there, of course, is the lack of data. So you're absolutely right. It's almost never the case that for your particular language pair that there is no data. I mean, you do hear people say that for my language pair of choice, there is no data. I don't believe that for a start, because if I was interested in a particular language pair which really did have no data, I would start to assemble a small team to produce some data. You just type it in, and after a month, you'd have a few thousand sentences, which may be enough to sort of trigger the building of a system. But I think, Doran, one of the areas in which can try to help low resource scenarios is this technique called back translation, where you reverse the directionality of the MT system and you expose it to lots of new target language text. You get that translated into the source, you switch the data back, and you augment your authentic human produced data, with this back translated data. And in all the experiments that we have run in low resource scenarios, adding back translated data appears to significantly improve the translation performance. So I think that's one way which seems to work. And I know that during the week you had a talk on zero-shot multilingual aspects of machine translation in low resource scenarios. So even in closely related languages, if there's data, that can be useful itself. I remember an experiment that we ran. We wanted to build an English Azeri from Azerbaijan, the Azeri language, and there was no data. But Azeri is a Turkic language, so we had lots of Turkish data. So we built an MT system to go from English to Turkish, and then we had a Turkish to Azeri dictionary. And again, the syntax is very similar, but the lexicon is quite different. And we replaced the Turkish words with the Azeri words, and the translations which ensued were reasonable Azeri translations. So I think there are some clever techniques that you can use in order to sort of bootstrap an engine to produce some output for some of those low resource languages. But we really need some of the voluntary organizations like Translators Without Borders are in dire need for people to actually start to produce data for the training of our models, because as I'm sure people have asserted during the week, without training data, machine learning doesn't even have a hope to start to solve these issues. So yes, the lack of training data is a big problem.
Thank you, Professor Andy. Is there any more questions from the participants?
Sir, excuse me. Sir, some machine translation can be used in fake news detection?
Sorry, I missed that. Can you use what?
Machine translation can be used in fake news detection.
Yeah, Doran, I didn't quite hear that. Did you hear it?
What he was asking is, can we use machine translation for fake news detection?
Oh, I don't know. I mean, okay. So it's undoubtedly the case that machine learning is being used to try to detect, and deep learning as well, to detect, like deep fakes, for example. But I'm not sure that machine translation itself can be useful there. I mean, one thing in that area, perhaps worth mentioning, is that there's lots of machine translated data on the web, okay? And in SMT, people actually they built software to actually find machine translated parallel data, and they made sure that would not be part of their training data, because people would think that because it's machine translated data, that would pollute the learning of the system, and the model would degrade in performance. But as I say, with the back translated data, that doesn't seem to be the case in neural machine translation. The fact that we have a lot of machine translated data and we add that to our human produced data seems to, across the board, improve machine translation quality. So I think that's another interesting difference between NMT and SMT.
Okay.
Excuse me. Yeah. First of all, thank you for this wonderful talk. I want to ask is, what does the similarity between scripts between two different languages play a role in the quality of the machine translation? And if so, can we improve it by using transliteration, by making both the languages in the same script?
Yes, that's two good questions there. Thank you for that. Yeah, so it's undoubtedly the case that the more closely related the languages are, the higher the translation performance. So if you were to build a machine translation system between Spanish and Portuguese, for example, which are very, very closely related languages, the performance improves. So, translating between English and Japanese, for example, is very difficult because the languages are quite dissimilar. And your second question there about the transliteration, yes, so we have done quite a lot of translation ourselves on Hindi, Bengali, Marathi, etc. And the first thing we have to do is make sure that we're using the same script. So we will translate the Indian language into, its kind of Latin equivalent in order to build the system. And then in order to output the translation in the correct script, we'd have a post-processing component so that people like you could actually then view that in your preferred Indian language. So yes, absolutely. That's a conversion process that we take on board in all of our Indian language processing components.
Thank you, sir.
Is there any more question from the participants, or we will just take one or two questions if there is any question? Okay, so if there is no more question, then let's thank the speaker once more for a wonderful talk and for clearing our doubts. Thanks a lot, Professor Andy, for having you with us today for this particular event and clearing our doubt and sharing your experience. Thanks a lot.
Okay, Doran, thank you for that. I was pleased to be here. Thanks for your questions and your patience in listening today. And I hope everybody enjoys the cricket this afternoon. So 2020 match is starting in 90 minutes. So it'll be interesting to watch that. Again, if I were face to face, then hopefully we could travel up to Ahmedabad and watch the cricket face to face.
Okay then.
Okay. Thanks a lot.
Okay.
Okay. Bye.
Bye.
Bye. Thanks, Aaron.
Bye.
Bye. Yeah.